Hello. In this video, we're going to talk about monatomic gases. Monatomic gases are the easiest of all the gases to talk about because they only a monatomic atom only stores energy as translation and electronic motion. So that makes developing the fundamental relationship a little bit easier. So for monatomic gases, we'll only need the translational and electronic partition functions, as those are the two modes of energy storage. To evaluate the translational partition function, we need the energy, and we've already developed that expression in our course on quantum mechanics. If the motion in the three coordinate directions are independent, then we can write the translational partition function as the product of the partition function in each of the three independent coordinate directions, and that is shown at the bottom of the slide. And here we come to taking advantage of the fact that the energy spacing, the translational quantum state energy spacing at any kind of realistic temperature is extraordinarily small. Remember that your sort of typical translational quantum number is 10 to the 8th or something like that, enormous numbers. And so making the approximation that we can replace the sum in the partition function with an integral is perfectly reasonable. And so that's the first equation on the slide, where we've just replaced the sum with an integral plus a dnx. So we're integrating over dnx. This is for the x direction, and we do exactly the same thing for the y and z directions. So if we let a new independent variable x be equal to the coefficient of n in the exponent, then we get the expression down below, and the integral in that expression is a well-known definite integral. It has the value of the square root of pi over 2. So the result is quite simple. It is that the translational partition function, and multiplying the three together, as we discussed, you end up with an expression 2 pi m, the mass of the atom, kt over h squared, all to the 3/2 power, times the volume. And it turns out that this is the only place where the volume appears, and it's due to the dependency of translational quantum states on the volume. We do need to deal with degeneracy. Recall that translational states are degenerate. And so if we're interested in energy rather than state, we need to account for the degeneracy. So we can define f of e dE as the fraction of particles in an interval epsilon to epsilon plus d epsilon. F of epsilon, which I keep calling E, it's energy, is a distribution function for the energy, and that can be written as using the Boltzmann ratios, e to the minus beta epsilon k over the sum of e to the minus beta over epsilon k, the sum over all quantum numbers, quantum indices, times dg. So to relate d epsilon to dg, consider that we can write the energy as h bar squared over 8mv to the 2/3 times n squared, where n is the total translational quantum number, and it's equal to the sum of the squares of the three coordinate direction quantum numbers. So it turns out that n is the radius of a 1/8 sphere in the positive octant of translational quantum number space. In other words, if you take an XYZ Cartesian coordinate system and then make a point where an X and Y and a Z are positive, n is the distance to that point from the origin of the coordinate system. And therefore, each state with energy between epsilon and d epsilon occupies a spherical shell of that 1/8 sphere between where n is between n and n plus dn, and the volume of that shell, dg, is 4 pi n squared dn over 8. So if you differentiate epsilon with respect to n, then you get this expression, and that is an energy distribution function for translational energy. Now, the translational energy is 1/2 mc squared, or v squared, depending on your notation. Typically, when talking about molecular or atomic speeds, individual speeds at the microscopic level, we use the term c for speed. So epsilon is equal to mc squared over 2. Therefore, d epsilon is mc dc. And if you want the speed distribution, which is where I'm heading here, you have to have that f of epsilon d epsilon is equal to f of c dc. And if you do that, you get the so-called Maxwellian speed distribution. This is a Gaussian function. Anything e to the independent variable squared over or under or over some other number is known as a Gaussian function. So the Maxwellian speed distribution is a so-called Maxwellian function, and we will run into this later, this idea. So here is a plot of the speed distribution. The average speed is just the integral of c f of c dc, and that turns out to be 8 kt over pi m to the 1/2 power. So that is translation. And then the other partition function we need is electronic. This is both simpler and more complex. There is no simple expression for the electronic states of an atom, as we have learned. Electronic motion is degenerate. And so basically you just have to do the sum. The partition function is equal to the sum over k, the quantum energy state index, of the degeneracy times e to the minus beta epsilon. In this case, we're summing over energy states rather than quantum states. So recall that nk is equal to e to the minus gamma beta, e to the minus beta epsilon k, and that n in the Maxwell-Boltzmann limit is e to the minus gamma sum over k, e to the minus beta epsilon k. So the probability of finding a particle in a given quantum state is n sub k over n, which is equal to e to the minus beta epsilon k over the sum over all the k's of e to the minus beta epsilon over k. And that's called the Boltzmann ratio, and that comes in very handy in a variety of applications. So just a number, just to drive home the fact that electronic energies are quite large compared to vibrational and rotational energies. So for nitrogen, the first excited electronic state has an energy of 19,227 inverse centimeters, and the ground state and excited state degeneracies are 4 and 10. So if the temperature is 300 K, then the Boltzmann ratio is equal to 1.67 times 10 to the minus 40. That's a pretty small number. So for most atoms, you can just make the assumption that the electronic partition function is just equal to the ground state degeneracy. If you have some low-lying electronic states, then you just have to perform the sum. But typically for normal thermodynamic system analysis, you might only have to add in 1 or 2 terms to the sum. So if you put all of this together, you can form the fundamental relationship. And here it is. This is the Massow function, in which we've replaced u with 1 over t and n with minus mu over t. And there is the function. This is the fundamental relationship for a monatomic ideal gas. And so we have the differential form of that relation is shown, and we know the Euler relation is shown. And so we can get the equations of state for the ideal gas. And it is interesting, for the first equation is the internal energy, and that's equal to 3/2 nkt. That's the so-called caloric equation of state. So the specific heat at constant volume is 3/2 NK. P over T, if you crank through, you get P over T. But if you calculate N, you get PV over KT, and that is the ideal gas law. Some other things you get from this, the average energy per unit atom, is 3/2 KT. Easy number to calculate. The entropy is K times 5/2 minus mu over KT. And so the specific heat, which is the partial of U with T at constant V, is 3/2 K. So some useful energy units. We've thrown around some of these before. So it is often the case that an electron volt is a useful unit of energy. It's the energy to move an electron through a potential of 1 volt, or 1.602 times 10 to the minus 19 joules. We talk about inverse centimeters. Energy of a photon is equal to h nu, which is equal to hc over lambda. So lambda is inversely proportional to the energy, and 1 over lambda is often called lambda prime. That's equal to the energy over hc, and 1 eV in units of inverse centimeter comes out to 8,066. So going back and recalling the expression for the Maxwell-Boltzmann limit, if we evaluate this for hydrogen, molecular hydrogen at 300 Kelvin and 1 atmosphere, the left-hand side has a value of 40,747, and that clearly satisfies the inequality. So that's it for this video. Thanks and have a great day.